Right. Okay, so team, until now, what have we learned? I believe you have been taught until TCP layer 4, right?
Yes, right.
Okay. So what have you understood so far? No problem if you are wrong. You can unmute yourself. You can tell what you have understood. This will allow me to understand what is to be provided.
We had learned about OSI layers uh, and DNS, TCP, and DORA process,
Hmm.
and TCP header,
Okay,
and also SSL handshake.
great. Yeah. So until TCP, everything is clear for everyone.
Yeah.
Great. So let me just present my screen to show. I'll just give a minute brief about IP header. I will not be completely theoretical because that is not the agenda. Just a minute. Okay. Is everybody able to see the screen?
Yeah, it's
Yeah.
visible.
Okay. So I believe in a similar fashion how you have learned regarding TCP header, the same way is how IP header is also is created, and there is a specification to that as well. So I believe the last session where I had explained regarding OSI, I told you that each and every layer, yeah, has a set of protocols in order to understand the consecutive layers among that. So if we see the OSI model here, so let's say if we are going from transport towards network or vice versa, that is from network to transport, these two layers should know what data they are carrying, right? And headers is something which allows that to be understood from, right? So instead of I'll just come to the practical part later on today. Today we'll just go simply based on each and every header and what each and every field means into a IP header, right? So I believe everybody is aware of what's the size of the TCP header. Any idea?
20 to 60 bytes.
Nice. 20 to 60 bytes. Exactly. So this 20 to 60 bytes, is it completely the size of the header? What's the base size? What's the
Minimum 20 and the maximum 60.
maximum 60 bytes?
Yes.
That's correct. Now, in a similar fashion, IP header is also having the same size, that is 20 to 60 bytes. So this is the standard, right? And this is just a header, just an informational header when it carries some data in it. That's it. So whatever size we are mentioning here, this is not the size of the data it carries. This is just the header size and the maximum header size it can have. Is that clear? Okay. Now,
Pardon, please, once again.
yeah. So what I was telling is these sizes are not the complete size of the data. Let's say that you are sending an image file. Okay, you are sending an image file to your friend. Let's say this is an image format, JPEG format. Okay, you are sending an image to your friend. Now when you send this image, there should be some information over it, right? Like how it should go, where it should go, what is the destination, which port it has to deliver the packet to, and all. So packet means the data in it, right? And something, yeah, and something which is added over it is the header, and that is what we add in the network layer, in the layer 3, which is called as IP header, right? And this one is again encapsulated with the TCP header, right? So on and so forth, this will be encapsulated, and then comes the protocols, right? So this is how it will be layered in a proper systematic order, and this is how the end host will decapsulate it. That is how they will understand that it has to go to this particular port. Let's say if you're sending this traffic to some random port, let's say 59,000 port, you're sending this traffic to. You send here, but to which particular IP address you want to send it, and that data you will get from the network layer, right? So this is where you will get the data from here. And then finally, the application will see that, okay, there is an image in it. Let's display the image to the end user. Now the user will be able to see the image based on this data. And that is the job of this header. So in simple terminology, headers does the job of attaching address, right? But in technical terminology, you cannot use this you cannot use this terminology for layer 4. You have to call them headers, right? So just to understand things, these are just appended things over data. So you can see here that there is some data which it is carrying, and the maximum amount of data that each header can carry is maximum up to 65,515. And I will come to the point how. I'll come later on now in 5 or 10 minutes how this particular number came, right? So this is how these headers and why they are important. Is that clear? Hello?
Yes.
Okay, so uh, right. So let's get on with the each and every field here. Now, if are you people taking down notes? Because today I will tell you some basic, just a basic gist of each and every field. You can take a note of that. Okay. Now you can make a note of this diagram as well, or you can take screenshot or make a note of it in your notebook if you're writing. Right now, coming to each and every this particular header, each and every field. Okay. In simple thing, as we see in TCP, there are totally 5 rows here, right, for each header, and each row is of 32 bits. That's the maximum size what each row can carry, right? And 32 bits, 32 bits, 32 bits, this overall gives you how much? So 32 bits is 4 bytes, because 1 byte is equals to 8 bits, right? So this 4 bytes of each, this whole field is of 4 bytes, 4 into 5, which gives you around 20 bytes of IP header. And this is how it is calculated, right? And the next header, the next optional layer, which each and every header has, is just a optional data. It can be used for research, or it can be used for any other task. Let's say you are into a core networking field, and you want to modify some of the data, or you want to modify this IP header altogether for your own benefit. You are developing a product, or you are doing some or the other things. So for that purpose, you can use this optional field, right? That is why it is optional, and that is why it has a buffer of 0 to 40 bytes. This is up to you how you will be creating it, but it doesn't mean that you can input any data here. It also has some standards. Based on that it will be done, but that's not relevant for this course, or whatever it is, right? Now I believe the size of the header is clear, and how each and every field is distributed is also clear, right? Now coming to each and every individual fields here, what we have. So number one is versions, right? So what does version do? It informs the preceding layer, preceding header, or else the header above it, that is TCP. So now we are talking about IP, and then we have MAC, right? Like this. So this particular version will tell to the layers which are beside it that which particular version it is carrying, which particular IP version it is carrying. Now, for this course, just remember that there are two IP versions, which is IPv4 and IPv6. We will come to the IP addressing just after IP header is completed. Maybe the next class or maybe the next. Okay. So IPv4 and IPv6. So there are two versions here. Okay. Now that's the job of this particular field here. Okay. Next we have the internet header length. What does internet header length tell? It just informs what's the size of the header altogether, not the data, right? Not the data, only the header size. Because as I told you, it is 20 bytes minimum and maximum 60 bytes. So in order to inform the other layers how much actual size of the header is, for that purpose this field is used, the internet header length. Simple. Next we have the type of service field. Now, its job is sometimes crucial and not that much important. But what it does is it just informs the preceding layers or just the layers above it or below it how much important this particular packet is. Now, let's say that you are talking to a end user over a video call, okay, and these are the streams of data that is going, okay. Now, what happens over here is that sometimes this end user might request, so this end user might request some data which is immediately required from this particular stream, right? So how will you do this in the layer 3? In layer 3, you will be using the type of service field. That is the moment the user clicks a button there, the type of service is modified, that is to high priority. Let's say this packet was required instead of this packet first. Now this type of service packet will have a flag as 1, which indicates that there is high priority to this particular packet instead of this, and this. And then this packet will be prioritized when it goes here. When this whole stream reaches here, the initial packet which will be provided to the end user is this packet. And then later these all will be executed, or they might be fragmented, and then they might be compressed into a readable format. Is that clear or this is confusing? Hello?
Yeah, it's clear.
Okay. So the number one is version, the number two is internet header length, then we have the type of service field which tells what's the priority of that particular packet, and then comes the total length. Now this total length, I told you that I'll come back to the point how this bytes of data came. This comes from this particular field. Now you can see here, this particular field is sized from 16 to 31 bit, right? So if you subtract this, you will be having overall 16 bits of data here. Okay. Now 2 to the power of 16 is this 6515, 65515. And that is how you are informing the other layer, that is TCP or MAC, how much data this particular IP header or this particular packet is actually carrying into it. Is it carrying the whole this much amount of data, or is it carrying less than that? You cannot go beyond this. I believe in the previous class you might have learned about window sizing, right? Window sizing, window scaling. Is it done?
Yes.
Yeah. So those factors are in conjunction with this. Okay. those work in the layer 4. They do their job in the layer 4, right? But IP also has a very minimalistic sort of a job here. What it does is it just carries this much amount of data. There is no window scaling factor, there is no window sizing factor here, because that job is taken care by TCP or the layer 4, right? So this is what is the job of this particular field, that is the total length field. It informs how much byte of data this particular header is carrying. Simple, right? So I believe this is clear, this whole row is clear. Version, internet header length, type of service, and then total length. Okay. And yeah, this is fine. And one more thing, the another thing is, for each and every field there is a specific uh, size to that. So this version field has only 4 bits of data in it, and this is standardized. The reason being, for version, max to max you will be either having an IPv4 IPv4 or IPv6. You will just annotate it in the packet capture, which I will show shortly, right? So for that, this much data is only required. Max to max 2 to the power of 4. That's it. This much data is only required. So only 2 to the power of 4 amount of data is required. That's the reason why the version field is having only 4 bits reserved for it. Then comes the internet header length. We are just informing what's the size of the header. So for that also we are just giving 2 to the power of 4 bytes of data. That's it. Then we have the type of service field. For that also we are using 8 to 16. So 8 bits of data, 2 to the power of 8. That's it. Nothing apart from that. So
Hello.
hello. Team, am I audible?
Yes.
Yeah, I had a power cut. Sorry, just a minute. Okay. So where were we? Okay, I was telling about what's the importance of the bits in each and every field. Why aren't they equal? So you might get questions when you are asked questions in interviews. They might ask you this simple question: Why? Why only this much size is required here? Why not a similar size what total length is required? This will be of no use, because this version is not being, this particular field is only being used to intimate what is the version of the IP you are carrying. Either you are carrying a version 4 IP or you are carrying a version 6 IP. That's it. IPv2, IPv4. We'll come to the IP addressing part later on, where we will discuss in depth about IPv4, IPv6, and then subnetting, and there are some additional topics. No worries, right? So I believe this whole layer is clear to everyone. Or do we have any doubts? Let me know. Let's clear that everything. It's confusing. Okay. Chalo. Now, now we have the next row, which is also 32 bits, right, or 4 bytes. So this is 32 bits is equals to 4 bytes, and the reason why, because 1 byte is equals to 8 bits. Simple, right? So that's it. Now, when we come here, when we come to the next row, we see that there is an identification field, we have flags field, and then we have the fragment offset field, right? Now, I believe you all remember in OSI, I told you that there is a concept called as fragmentation, right? What it does is it breaks the packets. Let's say you wanted to send around 70,000 bytes of data, right? Right? How will you send this byte of data when in fact you have the limitation of sending only 65,515 bytes of data only, right? In general sense, what do we do? Let's say if you have you know, a big stick is there and you want it to be transported to another state or another country, whatever it is, you cannot send this whole stick, right? You cannot send the whole pole or whole stick all together. You will cut them into pieces and then you will lay them onto the vehicle and then move it. Simple. Similar fashion, this is also what the fragmentation part does. So in IP layer, we call the division of these whole packet, which is in excess to the standardized size. We call that as fragmentation. Please make a note of this, fragmentation. In IP, we call it as fragmentation, and in TCP, we call it as segmentation, right? So
Abhishek, please help regarding that segmentation also. Yesterday I just forgot to explain on that.
got it.
Yeah.
Yeah, yeah. I'll come to that. No problem. So in TCP, we call the division of the packets segments or segmentation. So once the packets are divided, each packet is called a segment, right? And in IP layer, if there are packets which are divided, they are called as fragments, right? So that's the basic difference, and this is very important because interviewers will ask you questions, and during that time, they will concentrate on what terminology you are using when you discuss about layers. When they come to the topic of TCP, this question will probably come for anyone because this is related to performance, right? Your internet speed can be measured based on TCP, right? So during this time, there are many flags. So you might have gone through each and every flag there. SYN flag you have gone through. You have gone through reset flag, right? Acknowledgement flag. So these all mandatory flags are there. Along with that, when you divide the data, you segment. When you segment the data, so there are segments of those data in the TCP layer, and there are the maximum segments sizes there for a layer 4, right? And for layer 3 there is the maximum size for that as well, right? Now I believe We have not come to that point. Let's discuss one additional point here in order to understand this MSS, right? The maximum segment size. Now, in general, the maximum MTU is maximum transmission unit. How much data you can send via a wire. So at a time, you can send about this much bytes of data, which is 1500 bytes, right? Now, in this, if you remove the 20 bytes of IP layer header, which we are discussing now, and the 20 bytes of TCP layer, TCP header, right, which you discussed yesterday, this equals to 1460 bytes, right? So this is called the maximum segment size. That means that this is the amount of data which you can actually send to the end user at a time, because that's the limit here. That's the standard, and this is the standard protocol. In your home internet or in your office internet, we have this. Each cable is capable of only sending 1500 bytes of data at a time, right? That is called as maximum transmission unit, which includes even the headers. These are nonsense data. This is not required to any end user, because this is just a header what you are adding. That's it. Just to tell, okay, this is going to this particular IP address and it has to go to this particular TCP. Now, what is the actual size of the data? For actual size of the data, which is called as the maximum segment size, this is 1460 bytes. Right. So this is 1460 bytes. So I think this is what was missed in the last class. Please make a note of it for the TCP, under TCP. Right. And the next thing is, there is something called as jumbo frames. Right. These are extra topics, but this is something which you must understand in order to understand few concepts such as fragmentation, segmentation. Right. So there is a concept called as jumbo frame. Now, in Amazon servers, in Google servers, in Microsoft servers, we have lots of data which has to be transmitted at a time. Right? At a time, lot of data has to go and lot of data has to come back. Because you see, you are using YouTube, I am using YouTube, right? Multiple users are using YouTube at a time, and just 1500 bytes of data at a time, if it sends and it receives that much byte of data only, that's going to cause lots of performance issue. You will see that there is a lot of lag in the data what you are trying to request, even though you have a very high speed internet, right? That is how these big companies or MNCs, what they do is they use jumbo frames where their MTUs, they have a custom built MTU which is around 9000 bytes. So at a time they will be taking 9000 bytes of data. You understand the potential of this? Literally at a time, instead of 1500 bytes, look at how much times it has multiplied itself, around what, 8 or 9 times. So based on that, these are the two concepts what you must like make a note as an additional point, which is helpful. One is jumbo frame, one is MTU, right? Jumbo frames, let me make a note of this. MTU, jumbo frames, MSS, and fragmentation and segmentation, right? So these are some important concepts. Now, I believe, is this clear to everyone? Hello?
Yes.
Okay. You can make a note of this. You can do research at your end as well, because it's not easy to cover each and everything right now. If any doubts, you can ask me. Not a problem, right? So this concept should be understood to each and everyone. That is, what is MTU and what is the exact size of that. Okay, and then what is the MSS and what's the maximum size of that MSS. And later on in the course, I'll come back to performance TCP analysis using Wireshark. In that class, I will tell you how this MSS is actually causing performance issue and how can we improve performance. So that will help. For that to understand, you must understand this first. What is 1500 bytes? Why 1500 bytes? And why in TCP layer when we are checking the maximum segment size, why it is becoming 1460? The reason being we are just removing the headers. So to understand in basic terminology, this MSS is nothing but the actual byte of data. The actual byte of data. Right. Like this. Right? That's the actual byte of data. But MTU is not the actual byte of data. It is actual byte plus headers, TCP and IP. That's the reason why that actual bytes of data plus the headers is creating MTU. And this MTU is something which the wire carries. In Wireshark, I'll show you that. There is additional layer which will be additional 14 bytes which will be added here. And that is because of the MAC address which we add in the layer 2. So we are just discussing in layer 3 terminology. That's why just remember 1500 bytes. But when you actually go and analyze the Wireshark packet capture, you will see 14 bytes mentioned there. And the reason for this extra 14 bytes is nothing but your layer 2 device. Layer 2 device which is adding MAC. Right? These days there is no separate layer 2 device. That's L2, L3, both devices are same. That is your router nowadays. Not a problem. Okay. So that's the concept of MTU, MSS, fragmentation, jumbo frames. So these are extra concepts. Okay. Now why we discussed about fragmentation and IP fragments is this whole field is for that. Now let's say 70,000 bytes of data you are transporting. Suddenly you see that there is a limitation of sending 65,515 bytes, right? So you subtract the data and let's assume that only 500 bytes of data is remaining now. Now you see that the 70,000 bytes of data is removed, like 500 bytes of data is removed from 70,000. So 65,000 bytes of data went to the end user, right? And now the end user is waiting for another 500 bytes of data. How will they understand where to place that byte of data, what to do with that data? And that is what this particular field does. So when the data is actually divided, let's say the 70,000 is divided, this 65,000 once one part of data and 500 bytes one part of data will have a identification number attached to it. Let's say in R, for an example, I'm just mentioning it as A, and this one also as A. So this will indicate to the end user who is sitting here, who is trying to receive this data, he'll understand that, oh, these 2 bytes of data are same data. I just have to attach them together in order to comprehend it, in order to understand it. Simple. Now, what it does. So identification does its job of adding this identification flag. That's it, right? And flag tells that whether the byte of data, what you are sending, is that the last byte of fragmentation, or are there any more fragments which are coming ahead, right? So this particular header has 3 flags, 0, 1, and 2, right? Now this particular flag, what it does is it is a reserved bit, so you cannot change it, and there is no use of this. This is just reserved by INA, right? So that's the standard. So you can reserve. So that's just reserved, no use of that. But the next is telling us that whether we are trying to send the fragments or we want it to be, we don't want it to fragment. So this particular field tells us not fragment. So when this particular field is there, it tells that it is not fragmented. So let's say in our example only, this 70,000 bytes of data was going. Suddenly it got divided. Now this particular header, this particular packet will have more fragments flag as enabled as 1, right? One more point, guys. Here 012 does not mean that that flag will have 2 written in your Wireshark PCAP, right? So I am just writing 012 just for understanding purpose. However, there is no such thing there. It will be like reserved, do not fragment, and MF, which is more fragments. So whatever is equals to 1, this will stay 0. That you can leave. But if do not fragment is equals to 1, so that means that whatever byte of data is coming after this packet, there are no fragments. Simple. And if this is 1 and this is 0, this means that this particular, let's say in our example, I give MF is equals to 1 for this packet. So this packet, once it reaches this destination, so this end user will understand, okay, this particular byte of data is having an identification as A, and maybe I'm going to receive another byte of data of identification A, because there is a MF is equals to 1, right? That's how it will keep waiting for the next byte of data, this particular end user. Now this byte of data, once it goes to this user, here the fragment flag will be as 0, sorry, 1, and MF will be 0. Now what will happen? This end user will understand, okay, DF is equals to 1. So there are no fragments ahead. That means this is the last byte of data. Let me now start assembling it. Now how will it assemble? It doesn't know which packet goes first, whether this goes first or this goes first. Neither do you know, neither I know that. But who knows this? The end user who was sending the bytes of data. How will he annotate this? Like this is first packet, this is the second packet. That it will do using the fragment offset. Right? What does this fragment offset do? So when the bytes of data are like going like this, we see everything in packet format, right? So we see everything in packet format. So what will happen? This fragment offset will add its own offsets. Let's say 0 to 1, 1 to 2, 2 to 3. And then you divided these packets. Now when it is reaching to the end user, let's say the packets are reaching in this fashion, 2 to 3. So one packet reached. So this is the number one packet the end user got. Number 2 packet they got is 0 to 1. Right? So now the end user knows that fragments are there. That's good. Identification numbers are also there. That's good. And now he also knows how to attach this particular, or how to reassemble this particular packet, because he knows 0 is here and 2 is here, 3 is here, and 1 is here. So what that end user will do, he will tell not the end user per se, it will be the TCP or IP stack which will do this job for him or her, right? So 0 to 1 byte of data will come first, and 1 to 2 byte of data will come later, and 2 to 3 byte of data will come after that. That is how it comprehends the data, right? So here third byte of data will be 1 to 2. Is that understood? Hello?
Yes.
So that's the job of identification, just to identify the packet by identification. That's just the ID actually. I just gave you AA here, but it's an identification ID, right? The next job is flags, which tells whether to fragment it, whether to not fragment it, right? And then comes the fragment offset, which tells how the end user shall reassemble the packets. Because you and I both know that there will be packet loss. When I told you in the initial class that when it is traveling from one place to another place, you don't know where the packets will get dropped. And then packets has to go back again, right? And when the packets are jumbled like this, like 2 and 3 first, 2 to 3 bytes of data came first, right? 0 to 1 byte of data came later, 1 to 2 bytes of data came after that. So the job of end user is to check this fragment offset properly and then get it reassembled like this. That is how you will see the data. If we do not have fragment offsets, and if the TCP stack is not able to comprehend it, what will happen is this end user might have sent A to Z letters, and this particular end user will only see Z to A. because he doesn't know how to reassemble the packets. He's not aware of it. So that is how you are trying to inform the end user TCP stack that okay, you reassemble it like this. If by chance there is some delay or maybe you are not receiving the packets. Is that clear?
Yes.
Okay. Now, now what do we have next? Next, let's do this. So okay, now next row we have is the time to live, TTL, then the protocol and the header checksum, right? So it's very simple, not a problem, but this is important. This is simple. This is also simple, not that much relevant, but this is very important. TTL, right? So what is the importance of time to live? And please make a note of it. This is a very important concept in each and every field wherever you go related to networking. This value is supposed to be checked. With this you can comprehend a lot of things. You will understand a lot of things. I think current is hello.
Yes.
Team
Yes.
everyone.
Yes, you are audible.
Okay. Okay. So now that's the job of time to live. What it does, it avoids looping of the same packet within the network for infinite time of duration, right? How it does that? Let's say, let's assume, uh, okay. Now let's say there is a packet here, okay, and there are n number of routers around the globe there are n number of routers, and you are sending this particular packet. Let's say your IP address is 1.1.1 and you want to send the packet to 100.1.1.1, right? Now what happens? Let's say this particular is 2.2.2.2, 2.2.2.1, 2.2.2.3. Okay, so now you are sending the packets. Great that it goes here. Now this 2.2.2.2 tells that okay, you want to send the packet to 100.1.1.1. I do not have the address of that. Maybe 2.2.2.1 knows the address. The packet now comes here, right? Similarly, this guy also doesn't know where this address is. What it does, it sends the packet to the next hop, because this guy only knows that the next hop is this for him, or for this particular router. This is the next hop, right? So it sends the packet here. It also sends the packet back to this one, because it also knows that this is my neighboring router. Okay. Now you see what is happening. The packet is looping inside only. Nobody knows where this address is. Nobody is aware of this address, and this packet is going from here, and then it is looping like this. Now you have to understand one thing: when something keeps on moving within the network and it doesn't die, that will create network congestion. Like on our traffic roads and all, we see that vehicles are moving, right? And suddenly there is a halt, and the halt is because of n number of vehicles suddenly started coming. We don't know from where that came. We are not aware, but suddenly the traffic was jammed because of this n number of other vehicles. Regularly it was fine, but suddenly one day this happened. And that's the same story with network as well, right? The packet keeps on looping, and now there is some packet this guy is sending to 2.2.2.3, right? Then this goes to 2.2.1, and then this goes to 2.2.3, and the packet is delivered here. But there will be a lot of latency for this particular packet until it reaches this destination, and the reason being, the previous packet is still rotating. It is carrying certain bytes of data within the cable, right? within the router it is creating a lot of processes and all, and then unnecessarily it is utilizing all the process. That's the reason why the concept of time to live was introduced, right? Now what does this time to live do? Each packet when you send, there is a certain number what is set by your TCP kernel. Kernel means something which is in your core, in the base of your machine, in the base of your OS. So the base core structure of your OS is kernel, which has your TCP and IP stack. Now, what does this do? This will, for example, in Windows, we have the TTL maximum until, I believe it is until 64 or 120. I'm not sure, we'll check now. Okay, so what it does is this number, let's say we are taking, let's assume that there is a Linux device and it gives the TTL of 60 for each and every packet. What does this 60 indicate? This 60 indicates that after 60 hops, after 60 hops, the packet should die. The packet should die in the sense the packet will be getting dropped at the 60th hop. Let's say the packet here, let's say in our example only, the packet here to here, it went from hop to hop. So each hop from this router, so this first router, second router and third router, when it goes from first to second, that is considered as one hop. When it goes to second to third, it is considered as third hop. When it goes from third to second, again it is considered as fourth. So on and so forth. When it comes to 60th hop, right? Let's say at 60th hop it was here, let's assume. So here the packet will die. That means from here on the packet will not be sent here, neither it will be sent here. So you see the advantage there. It will not loop within the network and not unnecessarily consume the resources, right? So that is what TTL does, and that's the major importance of it and very important concept in the IP header. That's it. That's it about TTL. Now coming to protocol. So I told you in OSI model, there are certain things which headers tell to each other. So how will this particular IP header intimate to the MAC layer or the layer 2 layer that it is carrying some header into it, right? Some protocol into it. So in TCP, we carry protocols, right? TCP or UDP, right? So how will you inform the layer 2 that that I am carrying a TCP header along with me, or I am carrying a UDP layer header along with me? That job is done by this protocol layer. So it will have a field, it will have a number there. It will have 7 or it will have 16, right? And this 7 and 16 indicate the TCP and UDP numbers. So when it is UDP protocol, you will see 7, and when it is TCP protocol, you will see 16. Or maybe I'm wrong. Just a minute. It's not this. It's 6 or 17, which is 6 is TCP and 17 is UDP. So make a note of this. 6 and 17. So these are the protocol numbers also for this. For TCP, the protocol number is 6, right? And for UDP, the protocol number is 17. And make a note of it that these are IP protocol numbers, right? So that's about that. This is wrong. It's 6 or 17, and that is how the layers will identify which particular layer 4 protocol it is carrying. Okay, now coming to header checksum. So the job of header checksum is to verify whether all the data in it is proper. Simple, nothing apart from that, and not much of a relevance for that. It's just for to check if there is any transmission error. So just to check if there is the transmission is error free. In simple words, error free transmission for header checksum. For that purpose, we use header checksum. What it does is it will have a checksum value there. each and every IP header, if you'll see the packet capture, you will see a header checksum value. That header checksum value will be verified by the end user. Okay, this and that match. So there is no error into that. That's it. Simple. If it doesn't receive any particular header, let's say 1, 2, 3, 4, 5 header checksums went. 2 and 3 didn't receive. That is how the end host will understand that, okay, I have missed some 2 bytes of data. That's it. It will understand, but there is no uh, field like acknowledgement here as in we have in TCP. So it is just to verify in the network layer if there are any losses. That's it. That is why the header checksum is there. So based on this, the analysts can identify whether there was actually any issue in that. That's it. Okay. Now the next layers, the next rows, we have source address and the destination address. And this is just simple. Just now we saw what is the use of IP header. We are just attaching this with the data. So similarly, when we send an email, we have from and to. That's how these two layers are also doing. So we give the source IP address and we give the destination IP address and then send the data. That's it. And at each and every hop, let's say that you send from your system from 1.1.1 to 2.2.2.2, right? So the source will be this, destination will be this. Once the packet comes here, right? Once the packet comes here, the packet will be automatically modified to source as this and destination as again this, wherever it has to go, right? And then the packet goes here. Now the source will be what? 2.2.2.1 and the destination will be same. Now what will happen from here? From here, the same thing will happen. And once it reaches here, the packet has reached and then it will not loop in the network. So that's the importance of IP header. That's it. And this options field, as I told you, it's just a research field or something which we can add later on, not at all important. And data is nothing but what you're carrying along with it. Right? Any doubts?
How many bytes that source address will?
It's 4 bytes. So as I told you at the beginning, each and every field, each and every row is 32 bits. Right here, it's 32 bits. If you see this, it's 32 bits, right? Each and every field is of 32 bits. And
Okay.
that is equals to 4 bytes. So 1, 2, 3, 4, 5. These 4 rows into 5. That is 20 bytes. Right? Hello?
Yes, yes.
Okay, that's clear. Any further doubts? Okay, I think that's it for today. Uh, Before we wind up, just a second. So what I will do is stop presenting first. Yeah, I was about to show the IP layer.
Okay, in packet capture.
Yeah, I was thinking that.
Okay, okay. Continue.
I'll wind it up just a second. Okay. So before we just end the session, let me just show you how the IP header actually looks like. Okay. So is the Wireshark screen visible to everyone?
Yes, it's
Yeah. So I believe which frame 884. 884. Let's say I clicked on this frame here and let's try to analyze what it is trying to tell us. Right. So from previous sessions, you might have understood how it is actually working. Right. So you can see the complete OSI model here, or the TCP IP stack, whatever we discussed in the initial session. Now there is an application layer protocol which the TCP is carrying, right? Application layer, layer 4. This is the layer 4. This is sorry, layer 5. This is the layer 4, which is our TCP, and then our layer 3, which is our IP protocol, which we just discussed the IP header complete here. Now, if we see the IP header in a diagrammatical format, how we have just referred to, you can see this. So these are each and every headers. This is how actually Wireshark also interprets data. So you can see, I told you how the bytes of data is converted. You can see the size also. So 0, 1, 2, 3, 4. So 4 bits of data is for version flag, version field, and then 1, 2, 3, 4. 1, 2, 3, 4. 4 bits is for header length, right? If you click on header length here, you can see the header length. It is telling 20 bytes. So it is telling that this particular IP header is only 20 bytes. Now, if you come to differentiated service field or the type of service field, it is telling what type of services it is carrying with it, right? That is there. And then the important thing is total length. How much byte of data is it is actually carrying? So you can see it says 557 bytes here, right? And you can see that the TCP is telling that the total length is 517, right? So how it is calculating this overall bytes of data is, it's checking how much this is carrying. This is the 20 bytes of this layer and the length plus this. So 517 plus 20, right? How much is this? 537, and plus 20 bytes of this header, that is 557. So you see what I was trying to tell earlier. I told you that total length is the complete length of the IP header, the TCP header, and the application layer protocol, what it is carrying. So 557, we can see over here. It carries this particular transport layer along with it, along with that the TCP header and the IP header. So that's how it is. Next, I told you what is the role of identification, right? Identification, it is identifying that particular packet. So whichever packet I have selected here, you can see this packet here, its identification number is this particular hexadecimal code, 0xACC3, right? And whatever is in brackets, this is something Wireshark is converting that into numbers. That's it. So that is not relevant. Next, we see, I told you flags. So if I click here, you can see reserved, don't fragment, and more fragments, right? So I told you that if there is a packet and it says don't fragment and it has one, that means that after this packet, there is no further packets which are required, which the bytes of data will send. That is, there is no fragmentation happening here. And why is the fragmentation not happening? Any idea? Hello?
Yes.
Any idea why the fragment is this particular flag is set as don't fragment? So I told you that the maximum size the wire can carry is 1500 bytes, right? So you can see how much bytes of data this wire is carrying. It is carrying 571 bytes. Is it crossing the 1500 byte limit? No, right? And that's the reason why we have don't fragment set here for this packet. That means that we did not fragment the packet and there are no fragments there. Okay. And I would have shown you the fragmentation also, but time constraint, I'm unable to show it. We'll discuss that in the next class, or maybe I'll get a packet capture to show you that. Okay. So this is what the flags field does. And then we have fragment offset. As I told you, it shows if at all there were fragments, definitely you would have seen a number here and you would have seen 0, 1, 0, 0 for that packet, and then 0, 0, 0, 0 like that, right? And then you can see here time to live. So I told you that for each and every OS, each and every operating system, the time to live is different. So let's say in Windows it is 128, in Mac it is only 64, right? and in Linux it is lesser than that, or I'm not sure. We can check that. So in Linux also there is a certain time to live which is set in their TCP kernel. So that depends on OS to OS. But what's the use of time to live? After 128 hops, this packet will die. This packet will be dropped. That's it. There is no further hop to that particular packet, right? And then I told you what's the importance of protocol. It just tells what protocol it is carrying. So it is carrying, in this in our case it is carrying TCP. So we can see TCP, and in brackets it says 6, so that's the protocol number of TCP. And then I told you header checksum field, it's used for error free transmission. Okay, in our case, the end hosts, wherever we are trying to communicate or whatever packets I have captured here, these are not considering the header checksum field because validation is disabled. That depends on end host to end host. It is not in our control, right? You can use this header checksum field for different products, right? But in general scenario, header checksum is not used. So that is there. Now the next field is source address and the destination address, and definitely you are aware of this. That is, source is you. That's a private IP. I'll come back to private and public IP. That concept is yet remaining. And then the destination address. That's it. So this is something which I have added extra. We can discuss that at the end of our course. That's not important, but this is what is important. IPv4 protocol and the headers here, what we see. So that's it for today, guys. So you can basically, I believe everybody is using Wireshark. Just download Wireshark, try to set up your profiles like this. Just start the packet capture and check the basic things. So if you explore, that's when you will get a hands-on over it. Otherwise you will not understand anything, right? And I believe for layer 2 there is no separate class required. This is something which is added by your device, your intermediate device. Let's say in my case, TP-Link PTE, this particular MAC address is the destination MAC address. So that is where I am trying to send the packets to. And this is from where it is actually originating. So this particular MAC address is something which is related to my network interface card. So I told you that earlier, there are network interface cards on each and every machine, right? So that network interface card will have one MAC address. So this MAC address is sending the traffic to my router. So my router is TP-Link, with whose MAC address is this. So this is how the physical addressing works. And IP address is a logical address where we are sending the packets from one address to another address, right? I will, maybe in the next session when we have a little bit more time, I'll show you the IPv6 also. That's fine. So this is how it is, and frame is nothing but our basic wire. That's it. So from where, how much interface and all, and what kind of physical layer protocol we are using. Definitely I'm using Ethernet cable. So Ethernet is what I can see here. So these are something which you can explore at your end. This is not that important. But yeah. So, and one more thing is that in Wireshark, if anything is hard coded like this, it in brackets, this is something which Wireshark is providing you. It's not something which comes along with in the protocol. So this is just an extra header, what we see here, just for our purpose, the identification purpose, and how much bytes of data is actually going on the wire and all. So that basic data is captured and showed to us here, right? So that's it. So that is what the OSI or TCP IP model is. Physical, then the data link layer, then the IP layer or the network layer, and then the TCP IP layer, that is the layer 4 transport layer. And then we have the application layer where we can see the SSL protocol starting, that is client hello. So I believe this session is over. You can comprehend this, right? And this is something extra which has come because of the application I'm using. That's not important. Okay. So I believe that's it for today, guys. I think it was too much, but I hope you got to know something or the other from today's class. What I want you to do is try to learn a little bit more about this protocols, the IP header, TCP layer, and application layer. Just revise it properly so that the next session is easy for us to understand. And next we will most probably be starting with the IP addressing. part like what is a private IP, what is the public IP, how to do subnetting. So those all concepts are still there and they are remaining. So we'll come back to those maybe in the next session. As of today, I think that's it. Any queries, any doubts?